All right, here we go with the introduction to probability. We'll see how this works, and hopefully it goes well for you. Don't forget to pause, slow it down, back it up anytime you need to. All right, so we're going to start by just generally defining what probability is. And it is the field, its theory is used to describe anything that happens by chance or any kind of likelihood of something occurring. So that's the initial definition. And we happen to assign in probability every possible event a number between 0 and 1, inclusive, meaning it can be 0 or it can be 1. It cannot go outside of those bounds, and that number is the probability. And we'll look at that a little bit more later as we go as well. We apply probability theory in many different sciences. You probably recognize a few of these. Some of you are sports fans, politics. Look at what's going on right now in the world. It's used all the time. Casinos, insurance, chance of winning things. This is a little bit old. And of course, there's some biology right there. And this is what I was talking about in terms of something I was going to point out with 0 and 1 again. So if an event is impossible, cannot occur, the probability of 0 is assigned to that. If it is guaranteed or certain to occur, the probability of 1 is assigned to that. And then the scale between the 0 and 1 is the rest of the probability values. So if it's the exact same chance of happening as not happening, that's 50-50 or 0.50. And if it's more likely to happen than not, then the probability will be between 0.5 and 1. And if it is unlikely or less likely to happen than it is to happen, it is between 0 and 0.5. So we're going to look at two different types of probability, theoretical and experimental. Theoretical, you do not have any observations at all, and experimental is based on what you actually have found after many trials. So coins, we've been flipping coins forever. The chance of getting a heads is 1 out of 2 or 50%. But if you were to flip a coin 10 times, it does not guarantee that it'll come up exactly 5 times heads. So experimental probability is what happens over the course of many trials. So if you flip a coin, say 100 times and you get 41 heads, then your probability is going to be 0.41 or 41 out of the 100. And tails would be 59 out of the 100. So here's an example of the experimental. For whatever reason, you dump 145 paper clips onto a 6 by 6 centimeter square PET paper. So that's how many I dropped. And when I was done, I had some time on my hands, so I counted, and 113 fell inside the squares and 32 were not. So if I wanted to calculate the experimental probability of a paper clip landing inside a square, it's based on my actual results. So this would be 113 out of 145. And if I type that in my calculator, that's about 78% or 0.78. And landing on a line would be the 32 out of the 145 that I dropped. And that would be about 22% or 0.22. So pause it, give this one a go, and then we'll check the answers. All right, here you go. So 20 to 39 seconds is this little group right here. So that'd be 38 out of the total. So you'd have to add those all up to get your 78. Between or more than a minute, that's just this little group right here. So that'd be 4 out of 78. And there's your approximation. And between 20 and 59, notice that's two different groups. So that's both of these groups. So I'd have to add those together out of the 78. And that's how you get your experimental probability of TV commercial lengths. All right, so now we're going to talk about sample space. Sample space is the set of all the possible outcomes of an experiment. Sometimes it's referred to as U, the universal set. So it's basically everything that can happen, all the possible outcomes. There's a lot of ways to do this, and eventually we'll have looked at all of these. Today we're going to kind of focus on these first three. So if I want to just list the outcomes of tossing a coin, it's pretty quick. I use this U for my universal set. I put these cool little brackets, and the possible outcomes of tossing a coin, I could get a head, or I could get a tail, and that's it. That's my possible outcomes, pretty quick. So you're going to try doing that with the possible outcomes from rolling a 6-sided die. Pause it, check it. All right, you should have gotten outcomes of 1, 2, 3, 4, 5, 6. So we're also going to look at this thing called a two-dimensional grid or tables to illustrate possible outcomes. So if I want to do that with tossing 2 coins, if I want to make a two-dimensional grid, I could list my possibilities here. That's coin number 1. I guess I'll kind of do this. And coin number 2 would be a head or a tail. And then there's my grid. And then I could look at outcomes if I wanted interested in how many. So first off, I have 4 outcomes because there's 4 dots. If I was interested in the probability of getting heads on both flips, that only occurs right here where I have a head and a head where they meet. And so that would be 1 out of 4. Very similar if I wanted to make a table of this. Instead of putting dots, I could list my head and tail on the outsides here. And then if I want to come up here, I could go, oh, so my outcomes would be getting a head and a head. Here it would be a head and a tail. And I guess I'll use the one on the left first. So tail and head. Over here it would be a tail and a tail. And here it would be this head and this tail. So again, I have 4 outcomes. This actually has captured my true sample space right here. All the possible outcomes and all the combinations. Again, it's still 4, and there's my getting 2 heads in a row. Is only HH only happens once, so it'd be 1 out of 4. So that's kind of using a grid and or using a table. You get the same information. So you're going to try that to do the possible outcomes when you roll 2 dice. So pause this video and try to make one or the other or both if you're really excited about this. All right, here are your possible outcomes for your grid. Again, you have 1 through 6 from first die, 1 through 6 second die, and all these dots would be the possible outcomes. If you did it with a table, 1 through 6, and you could put this on the top or the bottom, it doesn't matter. And then this actually captures your sample space in here, which you'll notice is the same as this sample space over here. So these are your possible outcomes. Now, a lot of times when you roll 2 dice, you don't care that it's a 1 and a 1, or say a 6 and a 1. You care about what they add up to. So sometimes you could see a grid like this by rolling 2 dice. Instead of listing the actual value of each individual dice, you're looking at the total for each dice. And you'll notice that in this case, both with the grid, this table, and this table, there are 36 possible outcomes when you roll 2 dice. And it looks here 7 is highlighted because that's the one that occurs the most often. Getting snake eyes or 2 1s or getting 2 6s are the things that occur the least frequently, least likely to happen. All right, now we're going to look at creating a tree diagram, and I apologize in advance for how messy this is going to be because I'm tossing 3 coins, so I've got to throw 3 coins. So my first toss, I make a tree, is basically making these little branches here. My first toss could have ended up in a heads or a tails. That's toss number 1. I'm going to change colors just to make things exciting. Then I could toss the coin again, and I could get a head or a tail. Or if I had gotten a tail to begin with, I could get a head or a tail on my second toss. So that's toss number 2. And if I'm, for some reason, just want to keep doing this, there's toss 3. Again, luckily there's only 2 outcomes at each toss. So this is why I apologize. I kind of get things jammed up in here. This is the downfall of the tree diagram. You have a lot of things going on. You run out of space very quickly with your tree branches because, again, just like a real tree, it just keeps expanding. So that would be my 3rd. And then I can list all my outcomes by going along the branches. So this idea of going along the branches is very important. So my outcomes could be that I got 3 heads in a row, or I could have gotten heads, tails. So this is a very nice way to identify all your possible outcomes. Or I could have gotten head, tail, head. Or I could have gotten head, tail, tail. Same down here, I just follow the branches. I could have gotten a tail first, followed by 2 heads. A tail first, then a head, then a tail. Tail, tail, head. And then 3 tails. Let me make that H a little better. So now I can see that this is my sample space, and there's 1, 2, 3, 4, 5, 6, 7, 8 outcomes, 8 possible outcomes. And if I was interested in what's the probability of getting exactly two tails, well, this has 2 tails, this has 2 tails, this has 2 tails, and that's it. So that would be 3 out of 8. And you could go any combination of heads and tails to figure out the probability of those things happening. So that's how a tree diagram can help. So you're going to try that. I'm going to try to move this a little bit so you might be able to see it a little better for a second, at least. So you're going to use a tree diagram to illustrate the possible outcomes when drawing 2 marbles from a bag containing many red, green, and yellow marbles. So you're going to have 2 draws instead of 3 like me, and you have possibly drawing red, green, or yellow. So red, green, or yellow, and you're just going to draw twice. Pause it, check it. All right, so your first draw could have been red, green, yellow. Your second draw after each of those could have also been red, green, yellow, and so your outcomes could have been 2 reds, a red, a green, a red, yellow, etc., etc. So this is your sample space over here. All right, now we're going to talk about theoretical probability. And a theoretical probability, it's what you would expect to happen in theory. It's not a guarantee. Again, your experimental outcomes might be different, but in this particular situation, I have 8 geometric shapes that are all equal in size, and assuming the spinner is not rigged, each opportunity for landing on a number 1 through 8 has the same chance of occurring, and that is 1 out of 8, 12.5%, or 0.125. Those are all equivalent. So again, if I wanted to find out the probability of obtaining a 4, that's 1 of the 8 outcomes, and we're assuming they're all equally likely. So this here is the actual definition of theoretical probability. It is, again, what we theoretically expect to happen, and it would be what you would get if you were to spin this thing hundreds and thousands of times. In the long run, your chance of landing on a 4 would approximately equal or gradually become 1 out of 8, or get really, really close to 1 out of 8. So what about if I wanted to spin a 6 or more? So again, the spinner had the numbers 1 through 8, so 6 or more, my favorable outcomes would be 6, 7, or 8, and that, again, there are 8 possible numbers on there, and so if each one is equally likely, I would have 3 out of 8. So these are my favorable results out of the possible results, and that is basically how you would calculate your probability. If is important that each event is equally likely possible in your results. And this is the official definition, probably from your blue formula packet. So number of successful outcomes out of the possible outcomes is your probability. So we're going to do it here for, again, you can't see this, but I have 3 green, so I'm going to help you out here. You have 3 green tickets, sorry. 4 yellow tickets and 5 blue tickets. So this is what's in a basket. And I'm going to see what the probability is of getting a green ticket or each of these possible outcomes. So first off, notice that I have 5, 9, 10, I have a 12. I have a sample space of 12. So for A, I've got 12 tickets in there. And I want to know the probability of a green one. So I come over here, and there are 3 green ones. So that would be 3 out of 12, which is the same as a quarter. So 25% chance that I would get a green one. B, green or yellow. So notice that green or yellow are these 2 things right here. So I have 7 possible likely or outcomes that I'm interested in out of 12. C, orange. You see orange over here anywhere? I don't. That is impossible. I cannot get orange unless I were to try to merge these colors together, but I'm not going to do that. So no chance of it happening. And then finally, green, yellow, or blue. And so this word or is pretty important, and we'll talk about that as we move through this. Green, yellow, or blue, that would be any of these. And so that if I add all those up, that's 12 out of 12 and 1. So if I just said what's the chance of getting any one of those, it would equal 1. I do want to point out on this one real quick over here that if I just look at the green, which I already calculated was 3/12, and I look at the yellow, that's 4/12, it is not a shock that those add up. All right, you're going to try this and pause and then check your answers. And here are your answers. Take a look at them, see what you think, because this video just